Dear students, welcome to my channel Explore with Jahid. In today's lecture, we learn about atomic absorption spectroscopy. So let's start. Atomic absorption spectroscopy is a technique for determining the concentration of a particular metal element within the sample. The technique was introduced in 1955 by Walsh in Australia. Atomic absorption spectroscopy can be used to analyze over 60 to 70 different metals, including most of the common rare earth metals in concentration range of parts per million to parts per billion. Now we'll see the basic instrumentation and working principle of atomic absorption spectroscopy. So here we can see this is the hollow cathode lamp from where light is produced. This is the chopper which produces intermittent light, and this is the burner or atomizer. You can see the solution here, that is our sample, and from this sample this solution is atomized into solid residue, then molecule, then burn in the burner, and this is the monochromator which get the transmitted light and convert it into one single wavelength, and this is the focusing convex lens. We know the convex lens will ultimately trigger the different light into one direction, and this is the photocell which will ultimately produce current or electricity when light will uh, collide with it, and this is the detector which will ultimately determine the absorbance, and using the Beer-Lambert law it will ultimately determine the concentration of the analytes or the heavy metals. So this is the overall instrumentation of our atomic absorption spectrometry. So now we will see the working principle step by step, and we'll see how these overall components are working together. So first of all, electricity need to be produced, that is the incoming light need to be generated, and for this we can see here, if we apply voltage then light will be produced. You can see the light has produced upon the applying of voltage, and the chopper will ultimately convert the light into an intermittent light. Okay, you can see this was a continuous light and this was an intermittent light. Okay, this is one of the conditions for atomic absorption spectrometry. Then it will pass through this burner, and ultimately monochromator will produce a single light which will ultimately pass through the lens and fall into the photocell, and the function of the photocell is to convert the light into electricity, and this electricity will be measured in the detector and recorder. Okay, so in the recorder we will ultimately see the absorbance using the Beer-Lambert law, and this will ultimately determine the concentration of the heavy metals in this solution. So this is the overall mechanism and instrumentation of atomic absorption spectrometry. So here are the basic equipments of atomic absorption spectroscopy. These are radiation atomizer, monochromator, detector, and readout device. We will discuss this one by one. First of all, radiation or light source. The light source is a hollow cathode lamp. It consists of a tungsten anode and a cylindrical hollow cathode made up of elements to be determined. These are sealed in a glass tube filled with an inert gas, for example neon or argon. So you can see here usually anode and cathode exist in this hollow cathode lamp. This is the filler gas, and this is a quartz window. Now we'll discuss step by step mechanism for the emission of the light source. So first of all, ionization. The inert gas atoms are ionized by applying a potential difference of 300 to 400 volt between anode and cathode. We can see here, first of all, inert gas atom has been ionized. We know the ionization potential helped in this regard. The next step is sputtering. The gaseous ion bombard with cathode and eject metal atoms from cathode in a process called sputtering. We know this is a gaseous atom that has been produced. This will bombard the cathode. Okay, we know cathode is negatively charged, and after that it will eject metal atom. Okay, this is the function of the cathode, to eject some metal atoms whenever it will get bombarded with any gaseous ionized atom. After that, what will happen after the bombardment? The collision of sputtered metal atom with the gaseous ions result in excited metal atoms. Okay, so we know the sputtered metal atom has been produced from the cathode, and it will collide with the gaseous ions in the excited metal atoms. Okay, it will again collide with the gaseous uh, metal atom because it has been radiated from the cathode. Okay, and neon ion is already in the vacuum, and it will collide with the metal atom. The last stage is emission. The excited metal atom then emit radiation characteristic of the metal as they fall back to the ground state. So you can see here it will again come into the ground state because this is the excited state, which is very unstable, and it will again come into the ground state. Okay, and whenever something is coming into the ground state, it will emit radiation, and we know this radiation is the source of the light. The shape of the cathode is such that it concentrates the radiation into a beam which then passes through the quarters window. The shape of the cathode also facilitated the redisposition of sputtered atom. Okay, so this is the overall procedure for emitting radiation or light from the hollow cathode lamp. Our next component is atomizer. The function of the atomizer is to convert the atoms of the liquid sample into free gaseous atoms. The most common atomizer is flame. The flame breaks the liquid sample into droplets, which are then evaporated and leaves a solid residue. The residue is decomposed to give free atoms. These free atoms then absorb radiation characteristic for the particular metal liberated from the radiation source. So here we can see actually what is happening here. If we discuss one by one, we'll find out that first of all, the liquid sample, the solution will be converted into droplet. After the droplet, it will give rise to solid residue, and this solid residue will again convert it into free atoms. So from liquid to droplet, then droplet to solid residue, then solid residue will convert it to free atom. Thus we get the free atoms step by step mechanism. So we'll also discuss this in the principle of atomic absorption spectroscopy, which will be discussed in the upcoming slides. So here we have shown the figure once again. This is the hollow cathode lamp, and from the lamp, radiation is actually getting produced, and it comes into the atomized metal, and we get the transmitted light, which comes into the monochromator and ultimately detected by the detector and recorder. Then the monochromator is used to select the specific wavelength of which is used by the sample and to exclude other wavelengths. Most monochromator are prisms and gratings. Here we can see the overall functions of monochromator, that here are a number of radiations, but monochromator will ultimately convert into single one. And our last component is detector. The detector used in a photomultiplier tube. Its function is to measure the intensity of radiation before and after absorption by the sample. From this, we can calculate how much radiation has been absorbed from the intense beam, and that will be proportional to the concentration of the sample. Now we'll discuss the basic principle of atomic absorption spectroscopy. The principle of atomic absorption spectroscopy is based on energy absorption during transition of electrons from one energy level to another energy level. So this is the same principle as that for UV and fluorometry. Okay, the lower energy electronic configuration of an atom is known as ground state, and when energy is provided, outer shell electron are promoted to the higher energy state level. Okay, this is the common phenomenon as that of UV and spectrophotometry. We have already read about this. So here the ground state and excited state has been shown. We can see here when energy is getting absorbed, then it is coming into the excited state, and from the excited state it will again come down into the ground state by emitting radiation. So let's discuss the principles step by step. First of all, sample solution is atomized in an atomizer. Then droplet of the sample solution evaporates in flame, giving solid residue of the sample. First of all, we can see here that our sample was in solution form. Okay, then it converted into droplets of sample solution. Okay, that is solid residue is being formed, and this residue gets evaporated and solid sample molecule converts into gaseous sample molecule. Okay, then solid is getting converted into gaseous sample molecule. Okay, after that further gaseous molecule dissociate to give gaseous neutral metal atom. So now what is being produced? Neutral metal atom. So after that, due to flame temperature, some of the ground state gaseous metal atom will be excited, but most of atoms remains in the ground state and or unexcited. Okay, so now some of them will be excited. The electromagnetic radiations of particular wavelengths are passed through this ground state gaseous metal atom, which will absorb those radiation. So this is the overall principle of atomic absorption spectroscopy that we have already discussed. Let's see the principle in infographic show. First of all, that was in solution form. So it was aspirated into aerosols, then solid residue is being formed, and it was vaporized in flame. Then gaseous molecule is being formed. Then it was thermally dissociated into ground state gaseous sodium metal atom. Okay, we can see here that was in solution form, then aerosol was formed, then molecule was formed, then atom was formed. So we need this atom. Okay, so incoming radiation will come through this atom, and the transmitted radiation will be detected in detector. So this is the sample for atomic absorption spectroscopy. But think yourself that in UV and fluorometry, what was our sample? I think in UV visible spectroscopy and fluorometry, our sample was solution. Okay, our sample was this. But in case of atomic absorption spectroscopy, our sample is the atom. Now let's see the application of atomic absorption spectroscopy. First of all, clinical analysis, analyzing metals in biological fluid like blood and urine. Okay, so this is especially useful for metal, but one of the limitation of this spectrometry is that it cannot be used for non-metal. Okay, then environmental analysis, finding out the level of various elements in river, seawater, drinking water, air, petrol, etc. Then in pharmaceuticals, in pharmaceutical manufacturing process, minute quantity of catalyst is often required, which may be present in the final product. Besides, these are pharmaceuticals containing metals can be analyzed. Okay, like antacid, we know in antacid we use, for example, different salts. Okay, for different metals, salt of different metals we use as antacid. Like in total parenteral nutrition, also there may have some presence of heavy metals. Okay, moreover in laxatives like aluminum hydroxide, magnesium oxide. Okay, we also use metals. Moreover, there are some metal drugs like ferrous sulfate. Okay, or the iron tablet or calcium tablet. These are also drugs containing metals. So in determining these drugs, this atomic absorption spectroscopy is suitable, but these are not so much suitable for UV or fluorometry. Then in industry, raw materials are examined by atomic absorption spectroscopy to check the presence of major elements and often toxic impurities. In mining, by using atomic absorption spectroscopy, the amount of gold in rocks for example can be determined. Now let's discuss the advantages of atomic absorption spectroscopy. First of all, simplicity. The principle of measurement is very simple. Okay, because in case of UV spectroscopy, what you have to do, you need to first of all, if I provide you a tablet, then you need to crash the tablet, then you need to prepare the solution, then you need to dilute it for a very minute level, then you have to impart it into the uh, UV spectrometry. So this is the overall step-by-step procedure. But in case of atomic absorption spectroscopy, the sample is somehow can be no requirement for dilution. Okay, no requirement for dilution, and this is very easy. Then widespread application. This is used widely for quantitative determination of most of the metals. Then sensitivity. Okay, metal can be analyzed at a level of ppm and even ppv, parts per billion. You can see 10 to the power minus 9. Okay, parts per billion means microgram per liter. Okay, which is very low concentration. But UV or fluorometry can be used in analyzing at a level of ppm. Okay, but atomic absorption spectroscopy can be used even if for ppb. Then interference, it is possible to determine the metal in the presence of other metals without any interference. Then the technique is relatively inexpensive. Then equipment is easy to use. However, there are some disadvantages of this spectrometry. First of all, it is sequential. A separate lamp for each element is needed. Okay, this is one of the common limitation. So it's suitable for small scale measurement. Then it's applicable for only liquid sample, not for solid or gases, because one of the steps that we have learned in the principle section, we have seen that it need to be sprayed. Okay, so liquid sample can only be sprayed, but you cannot spray solid or gases. Okay, in the aerosol we use the aerosol, and within the aerosol container we see the liquid products. Okay, not the solid or gaseous product. Okay, so it's easily relies on sample dissolution in solvent. Moreover, it's not applicable for determination of non-metal. However, there are two types of atomic absorption or atomic emission spectroscopy. Atomic emission spectroscopy is also called flame photometry. Okay, so these are both atomic techniques and can be used for analysis of soil, food, water. Okay, so both of them are much more similar, but the basic difference is in their principle. Okay, it is an emission spectroscopy and it is an absorption spectroscopy. So measurement of emission radiation is the basis, and measurement of the absorbed radiation is the basis. And emission of radiation depends upon the number of gaseous excited metal atom, and in this case, number of gaseous unexcited metal atom. Emission phenomenon depends on flame temperature. Absorption phenomenon is independent on flame temperature. Only limited to alkali or alkaline earth metal, and this can be used for approximately 70 elements. Okay, so this is very useful. So these are all from our atomic absorption spectroscopy. If you have any confusion, please inform me in the comment section. Thank you.